Hello everyone, my name is Marcel Beetz, and I will be presenting our work on predicting 3D cardiac deformations with point cloud autoencoders. Mechanical deformation of the heart plays an important role in the assessment of cardiac function. In current clinical practice, only approximate 2D-based biomarkers, such as stroke volume and ejection fraction, are often used to evaluate cardiac mechanics. This limits the success of cardiac diagnosis and treatment, as biomarkers that require three-dimensional models of cardiac dynamics are not taken into account. Consequently, there is a clear need for accurate models of 3D cardiac deformation. In this work, we aim to develop a deep learning model capable of predicting 3D cardiac deformations between the extreme ends of the cardiac cycle. This is a challenging task for multiple reasons. First, cardiac deformation is a complex, nonlinear 3D process that exhibits significant interperson variability. Second, deformation patterns differ considerably between cardiac contraction and relaxation. Third, both global and local changes are important for a holistic evaluation of cardiac mechanics. Fourth, the underlying data acquisition of a standard cine MRI is often based on 2D slices, despite the inherent three-dimensional structure of the heart. This makes robustness against artifacts a necessity for any method attempting to predict 3D cardiac deformations. Finally, low per-case prediction times are needed to allow efficient clinical use and scaling to large population cohorts. In this work, we propose a novel point cloud autoencoder architecture to predict 3D biventricular deformation from the end diastolic to the end systolic phase and from the end systolic to the end diastolic phase of the cardiac cycle. The network follows an encoder-decoder structure and works directly on point cloud representations of the multi-class biventricular anatomy. We extend the point-net++ and point completion network architectures to our multi-class high-dimensional setting and use them as the encoder and decoder of our network respectively. The output of our network consists of a coarse, low-density point cloud to predict the anatomical surfaces on a global scale, and a dense, high-resolution point cloud that aims to accurately represent the predicted biventricular anatomy on both a local and global level. The dense output point cloud is used as the final anatomy prediction of our method. The loss function of our network consists of two loss terms weighted by a parameter alpha. The coarse loss term compares the sparse output point cloud of the network to the gold standard point cloud, while the dense loss term calculates the difference between the dense output point cloud of the network and the gold standard point cloud. In both cases, we choose the chamfer distance between the two respective point clouds as an approximate surface-to-surface distance between the biventricular anatomies. At the beginning of training, we use small values for the weighting parameter alpha to put more emphasis on the coarse loss term, which encourages the network to capture the global anatomical surface. We then gradually increase the value of alpha as training progresses to improve the network predictions on a local level while maintaining a good accuracy on a global scale. We randomly select 1,000 cases of the UK Biobank study and split them into a train and test dataset for method development and evaluation respectively. We train two separate networks, one to predict the biventricular anatomy at end diastole from the corresponding biventricular anatomy at end systole, and another one to perform the same prediction task in the opposite phase direction. When visually comparing the results, we observe that the predicted point clouds and the gold standard point clouds of the test dataset align very well on both a local and global level and for both prediction tasks. We also find that our method is capable of accurately processing a considerable variety of heart shapes and deformation patterns. In order to quantify the prediction performance of our method, we calculate the chamfer distances between predicted and gold standard point clouds on the test dataset. We find very good prediction results for both prediction tasks and all cardiac substructures with distance values similar to the voxel resolution of the underlying image acquisition. Next, we want to assess the prediction performance of our method from a clinical perspective. To this end, we convert both the predicted and gold standard point clouds into meshes using the ball pivoting algorithm and calculate common clinical anatomy and function metrics for each mesh population. We find very similar scores for the predicted and gold standard meshes in terms of both means and standard deviations and across all analyzed metrics. Slightly better scores are achieved for the prediction of end-systolic anatomies than for the prediction of end-diastolic anatomies. In the next step, we want to investigate whether there are subpopulation-specific differences in biventricular deformation patterns. To this end, we first select the binary variable sex to split our dataset into two subpopulations. We then train a network on only female subjects and compare the prediction performance of this network for female and male test cases. We find statistically significant differences between the prediction results of each sex for both prediction directions. This indicates that there are subpopulation-specific 3D deformation patterns that the network was able to successfully learn in order to improve its prediction accuracy for the subpopulations that it was exposed to during training. Overall, our method has several key advantages. It is able to predict complex, nonlinear 3D cardiac deformations with high accuracy for a variety of shapes and is applicable to both cardiac contraction and relaxation. No point correspondence or registration of the data is required, while the memory-efficient point cloud representations enable high data resolution. Our method is fast, fully automatic, easily scalable, and shows high robustness against artifacts. Furthermore, our network can capture subpopulation-specific differences in the cardiac deformation patterns and is capable of processing multiple cardiac substructures at the same time. However, our method also has some disadvantages. It requires an adequately sized dataset for training and was only validated on healthy volunteers. In addition, the predicted deformation patterns were limited to the extreme ends of the cardiac cycle. In summary, we have presented a novel, memory-efficient point cloud autoencoder that is able to predict 3D nonlinear cardiac deformations with high accuracy and extract subpopulation-specific deformation patterns. Thank you for your attention.